We have come to a new set of exercises. In here we are going to study symmetries of geometric objects, or rather groups of symmetries of a geometric object. So in the first one we have been asked to describe each symmetry in D3, which is the set of all symmetries of an equilateral triangle. So we can write the solution like this. Although it has been suggested that we use both pictures and words, the words I will say and the picture is here in front of you. So here what we have done, we have taken an equilateral triangle, and in each case, what is a symmetry? A symmetry is a kind of transformation, something that is done to an object so that the initial and final look of the object, they remain the same. If you ignore the vertices, the labels of the vertices, the triangles that you see here are identical. I mean, if you ignore the small imperfections, then the triangles are identical. We are giving the vertices some names to keep track of the transformations we are making them go through. Okay, so in the first one, we have performed something known as R0, which is actually not doing anything. It does not change any point of the plane. We are calling it R0 because it can be thought of as a rotation of the plane through an angle 0 degrees. So it actually does nothing. So that the vertices A, B and C, they stay in their positions, they remain in the same position. In the second symmetry, we have R60, which is rotation of the plane counterclockwise through an angle of 60 degrees. You already know that the internal angles of an equilateral triangle, each one of them is equal to 60 degrees. So if we perform that rotation, the axes will change their positions. However, each axis will take the place of another axis. Oh, sorry, I said axis, vertices. The vertices will change their positions, and for example, the vertex C will take the position of vertex A will come to B, and B will go to the position of C. So we will get this arrangement of vertices, but the triangle looks the same. It's I mean, what you can say, it seems as if nothing has been done to it. If someone is blindfolded and this transformation is applied, then if the blindfold is removed, that person won't be able to say whether the triangle has gone through some sort of transformation. So that is the meaning of symmetry. However, we can see, because we have labeled the vertices, that something actually has gone on, and specifically this transformation has been applied on the triangle. So this is R60. Just like that, R120 is rotation counterclockwise through an angle of 120 degrees. So essentially this is applying R60 two times. Okay, so on this one again, if you apply R60, you will get this. That is, we have ABC, now we have ABC. Okay, now in these three transformations, in the first one of course nothing happens. You can see that although the positions of the vertices have changed, but something has not changed, and that is the orientation of the vertices, in the sense that their cyclic order has not changed. We are talking about counterclockwise rotation, no. So although the positions have changed, here we have B, here we have A, here in the same position we have C, but if we start with any vertex, say we start with A, then we move in the counterclockwise direction. The next vertex is B. Here also after A we have B. Here also after A we have B. So the orientation has not changed. However, in the next transformation, the orientation changes. What is this transformation? It's the transformation that is a reflection. about this line, the perpendicular bisector of the side BC. We know that since this is an equilateral triangle, from elementary Euclidean geometry, we know that the perpendicular bisector will pass through A, and if we flip the triangle about that perpendicular bisector, all the points lying on that line, none of them will change, everything else will change. So B and C are interchanged, however A being a point on that line, it does not change. Okay, so here you can see, so what I was saying is that the orientation has changed. Why? Now if you move in counterclockwise sense, counterclockwise direction, after A no longer B is no longer coming after A. After A you are getting C. Only if you move in clockwise direction do you get B after A. So here the orientation has changed. For the other two also, that changed orientation is there. You see, you move clockwise, after A you get B. Okay, so it's like this. Here I have a triangle cut out. This is ABC. So here the sense is counterclockwise. If you look at the other side, maintaining the positions of these vertices, here you have A, on that side also you have A, here you have B, on that side also you have B, C, C. So if you change the way you look at the triangle, now the orientation has changed, ABC, now it is clockwise. So this cutout will help us shortly. So first we look at this thing. Okay, now we have understood this one. What about this transformation? This one can be obtained from this one by applying R60 on this one. So if you rotate this again counterclockwise through an angle 60 degree, then you will have ACB. See, ACB. If you do that once more, you get BAC. So these two transformations are like, each one of them is two transformations performed one after another. We start with this one, first we flip and then we rotate. For this one, V followed by R60. This one is V followed by R60 followed by R60, or V followed by R120. But the question is, are these two transformations really like that, or can they be described in somewhat easier manner? In fact, they can, and you can see that although we have made sense of these transformations as a flip or a reflection followed by a rotation, ultimately each one of them is a reflection, but about not this line, about some other lines. Looking at these two triangles, the initial one and the final one, you can see that the position of C is unchanged. However, A and B are interchanged. So naturally this is a reflection about this line, this perpendicular bisector of the side AB. Just like that, here since B remains the same, it is unchanged, and A and C are interchanged. So this is the reflection about this axis. You just reflect like this. Here you have ABC, oh sorry, this one, this side, ABC. I hope you can see ABC. If this is my axis of reflection, if I reflect like this, I get BAC, BAC. However, if this is my axis of reflection, then I get CBA, CBA. Okay, so These are all the symmetries in D3. Each one of them is an element in D3. How many do we have? 1, 2, 3, 4, 5, 6. That means 3 rotations and 3 reflections. In the next one, in exercise 2, we have been asked to write out the complete Cayley table for D3, which is a table that will encode information about compositions of these transformations or symmetries. Since each one of them is a function, they can be composed using function composition, and we have to figure out what the compositions ultimately give us, ultimately turn out to be. And in this, before we compile this table, I mean we already have it here, we have to make sense of the entries. Before doing that, let's make one thing clear. Here, for example, you can see from the way we have described C1 is actually V followed by R60. We will write that like this. R60V. R60V does not mean you perform R60 first and then V. It means you perform V first and then R60. It's like this. You have two functions, say F1 mapping A into B, A, B and C are sets, suppose, and G mapping B into C. Then the composition of F and G is written like this, and it's a mapping that maps A into C, and we write it like this. We write the second function first because when you calculate the composition, you write the input to the right of the function, no? So that makes us apply the first function first. To do that, we need F on this side, so that's why we change the order. Some people write the input to the left of the function, which is, however, is not followed in this book as far as I know. I mean, so far function composition is just like this, just like how we ordinarily write. So that's why this R60V actually means R60 composition V. We are not writing the composition in between, we are just simply writing R60V, but it means apply V first and then R60. Just like here, apply F first and then G. Okay, so in that sense we have to make sense of the entries of this table. Okay, so now let us come to the table itself. We have rows and columns. First of all, you look at the first row, it just has the entries we have in D3, that is these entries. R0, R60, R120, V, C1, C2. And maintaining that, there is no necessity for maintaining the order of the order of the elements in the rows and columns, but we just keep the same order because it looks nice. There is another reason also for maintaining the order, but it will be premature to say something about that. So here also we have R0, R60, R120, V, C1 and C2. Now what does this entry tell us? This entry is R0 composition R0. A better one would be to look at this one, say, this entry, say. This is R0 composition V. First we take the row, the entry in the row and then we take the entry in the column. So on this row we have R naught, in this column we have V. So R naught V. Now what is R naught V? We are applying V first. So applying V first means it flips the triangle above the vertical perpendicular bisector. Vertical means perpendicular, okay. But then on that if you apply R naught, nothing happens because R naught does nothing. So applying R naught V is the same as applying V. So that's why this is equal to V, and that's how we get this entry V. So it's like this. You have A, B, C. So you just flip and then that's it. Applying R naught to this is just this. I mean, it does not do anything. So R naught V is V. Okay. So this we have, let's just put the entries in circles once we have figured out how it has come. R naught is R naught because R naught 2 times it does nothing. That is as good as doing nothing just once. So R naught. You quickly realize that if you compose R naught with anything, you get that anything back. You perform R120 first and then on that R naught which does nothing, so it's the same as R120. So here you will get the same elements R60, R60. Each one of them has come as a result of a product where the first factor is R naught and the second factor is that thing. In the first column, the order is reversed. Here R naught comes as the second factor. For example, here this one is R60 R naught. Apply R naught first, which does nothing, and then you apply R60, which is the same as just applying R60. So here also we have R60, R120, V, C1 and C2. Okay, so these are trivial. Any composition with R naught is trivial. I don't want to wrap this part up, we will need this. R60, R60. What does R60, if you apply R60 2 times, then that means you are changing the, I mean you are rotating 2 times through an angle 60 degree. So this is ABC, you rotate 1 times, this is the arrangement. You rotate once more, you get BCA. BCA, which is the same as rotating through an angle 120 degree once. So that's why R60 is R120. Now if you perform for this one we have to calculate R60, R120. If you perform R120 first, okay, so this is 160 degree, another 60 degree, and then another 60 degree. So we get back A, B, C. That is the original arrangement of the vertices, which is the same as doing nothing. That means essentially we have made one complete revolution. Okay. Well, not one complete revolution, no, we haven't done 360 degree rotation, we have done 180 degree rotation. However, that itself has brought all the things back to their original position. So that's why this is the same as R naught. That's how we get R naught. And you can see that whether you do this by first performing R120 and then R60, or by first performing R60 and then R120, it does not change. You still get R0. So this entry also has been interpreted properly. Okay, then R60V. What about this one? With the help of our cutout, we can see quickly. R60, so this is ABC. R60 is this. And then V is flipping the triangle about a vertical axis. This. So CBA. CBA. So R60V is, oh, I think I made a mistake. Now first I have to apply V first and then I have to apply R60. Okay, yeah. So first of all, I have to flip. So that means I have to do this and then change, then rotate. BAC. So BAC. So this is C1, and that is why R60V is C1. Yes. Then R60C1, ABC, R60C1, but I have to keep in mind that I perform C1 first. So C1 means flipping about this axis, this, and then R60. CBA, CBA. So this is the same as applying C2. C2. Then R60C2. So this is ABC. So now we will apply C2 first. C2 is flipping about this axis and then R60. ACB. ACB. So this is the same as V. Okay. Do we check the other entries? I leave it to you to check the to verify that the other entries are also true. Let us maybe do two more. Say, for example, how do we get C2V equal to R120? C2V means first we will perform V. So this is ABC. V means flipping about a vertical axis, this. And then C2. C2 is flipping about this axis. So we get this, BCA. So you can see that here we have BCA. So which is brought about by the transformation R120. So that's how C2V is R120. And one more. Maybe say C1, C2 is again R120, R60, C1V. Okay, let us just see C1V. How is it R60? C1V. So first we perform V, this, and then C1. C1 is about this axis we have to reflect. So CAB. CAB, R60. So that's how we get R60. So C1 V is R60. So that's how you can make sense of the other entries also. So this is the complete Cayley table for D3, and it tells you what the result of each composition is. You can see all possible pairs, all possible products where two elements are involved have appeared here. Now next, is D3 abelian? D3 is not abelian because you can see from the table R120V is C2. R120 in the column of V you have C2, whereas if you change the order V R120, then V R120 is C1, and C1 and C2 are not equal because, for example, you can see they are not equal. Here you have B, here you have C, so it's not abelian. Why is symmetry important? Aside from the fact that symmetric objects are nice to look at, they are aesthetically pleasing, but there is an advantage also. You see that once an object is symmetric, then the symmetric sides are sort of equal in the sense that if you study one of the corners, it's equivalent to studying the other corners. Your job is cut down because of symmetry. If you know that something, whatever is happening on this side has a symmetric counterpart on the other side, then it's enough to study only this side. Automatically you can conclude things about the other side using that symmetry. For example, an equilateral triangle is symmetric. So this angle is 60 degree, the other two are also 60 degree. Something like that. Whatever happens to one side, the same thing happens to the other side. For example, if you draw the perpendicular bisector of the side BC, that is a line that is perpendicular to BC and bisects BC, then that line passes through the third vertex. That same thing happens for the other sides also because of symmetry. Here also, if you draw a perpendicular bisector, it will pass through the other vertex. So automatically you know that the same thing is going to happen for the what can I say? The other components which are symmetric to this component, or the other aspects of that object which are symmetric to this particular aspect. Okay, so that's why symmetries are studied, and the mathematics of symmetry is group theory. And the more symmetries an object has, the easier it is to study, or the less labor you have to put in studying the object, because it will have more components that are like that. For example, one component, okay, and its size also gets smaller and smaller. You have to study only a small part of the object to know about the other symmetric parts of the object, and hence to know about the whole object. And having more symmetry means having larger and larger symmetry groups. Here, an equilateral triangle has 6 symmetries. Something else which has more symmetries will be more symmetrical and hence easier to study in that sense. Okay, so next let us look at the next exercise. In D4, find all elements X such that and one more thing is that before we go to this third one, symmetry is not something that is I mean, it's not only about geometric objects. It can arise anywhere and in almost every aspect of mathematics, or in almost every branch, not almost, in all branches, you will definitely come across one or another form of symmetry in every type of object. And having a symmetry in an object makes it easier to understand. So that's why symmetry is very important. Such that a x cubed is equal to v. D4 is the group of symmetries of a square. Like D3 is that of a triangle, D4 is the symmetric group of a square, and its elements have already been discussed in the text, so we have those things. In fact, we have the Kelly table itself for D4. So from that table we will be able to determine these elements. C, x cube is R naught. D, x square is R naught. And finally E, x square is equal to h. For this one, I would suggest you to look at the Kelly table we have for D4 in the text. Looking at that table, you will see that the solution to this exercise is just this. X cube is V. There is only one choice for x which will give us that. That is V itself. V cube is V. For Bx is R120. No, not 120, sorry, 270. For C, x is just R naught. For D, x has many possibilities. These are all the possibilities. R naught, R180, H, V. The meanings of these symbols you can find in the text, in the Kelly table for D4. And for E, there is no x whose square equals h. No such x exists. Okay, so the solution ends here. To look for elements whose squares are equal to R naught, although we have to look at the Kelly table for D4 just to tell you what the thing means. Note that the squares appear along the diagonal of the table. R0, R0, R60, R60 here, R120, R120. So here you can see that along the diagonal, these positions, along this diagonal, which is known as the leading diagonal in many contexts. This is R0, this is R0, this is R0, this is R0. So Had the same question been asked for not d4 but d3, then the possibilities for x would be r0, then v, c1 and c2. Okay, here however these are the possibilities, many of them. R270 is not one of them. Okay, R270 times R270 is not R0 in D4. Okay, now next, exercise 4. And this one also I have to draw figures. Describe in pictures or words. Or words the elements of D5. Symmetries of a regular polygon. Not polygon, sorry, pentagon. Yeah, polygon is a general one.